Hey folks, welcome back again to Advent of Code in F#, and we are at day 16 already. Or at least if we skip the days I've skipped. So yeah, let's take a look at today's puzzle. The floor will be lava. With a beam of light completely focused somewhere, the reindeer leads you deeper still into the lava production facility. At some point, you realize that the steel facility walls have been replaced with cave, and the doorways are just cave, and the floor is cave, and you're pretty sure this is actually just a giant cave. Finally, as you approach what must be the heart of the mountain, you see a bright light in a cavern up ahead. There you discover that the beam of light you so carefully focused is emerging from the cavern wall closest to the facility and pouring all of its energy into a contraption on the opposite side. Upon closer inspection, the contraption appears to be a flat 2D square grid containing stuff, empty space, mirrors, and splitters. Okay, we have a grid again. The contraption is aligned so that most of the beam bounces around the grid, but each tile on the grid converts some of the beam's light into heat to melt the rock in the cavern. So we have a layout of the 2D grid, mirrors, splitters, and empty space. Cool. The beam enters in the top left corner from the left. Okay, so beam enters here. It heads to the right. Cool. Then its behavior depends on what it encounters. Empty space, it just continues in the same direction. Cool. Mirror, reflected 90 degrees, and we have two directions. Yeah, makes sense. If the beam encounters the pointy end of a splitter, the beam passes through as if it were empty space. Cool. If it encounters the flat side of a splitter, the beam splits into two, going in each of the two directions. Interesting. Cool. So if we hit this splitter sideward with a rightward moving beam, then it splits into two beams, one going up, one going down. Makes sense. Beams do not interact with other beams, and a tile can have many beams passing through it at the same time. Okay, so this is how a beam of light passes through. Goes to the right, goes up, but there's nothing there. It goes downward, splitter again, mirrors, bounce, 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 bounce. Splitter, I already see some cycles in there, so we can have cycles, cool. Beams are only shown on empty tiles. Arrows indicate the direction of the beams. Yeah, that's just how we visualize it. The same diagram, but instead only showing whether a tile is energized or not. What does that mean? Sorry, we skipped the energized part. A tile is energized if that tile has at least one beam passed through it. Okay, so we need to count the amount of tiles where a beam is passing through. Okay, doable. Let's take a look at our input. There are a lot of empty spaces. What would be the best data structure to represent our grid? We need to be able to look at spots, and we need to be able to like traverse the grid until we hit something. Best way would be a 2D matrix, but then we have to do some out of bounds checks. We could also use just a lookup table, mapping coordinates to whatever is on that coordinate. That could also work. It's a bit slower on the lookup, but that could also work. I think I'm gonna try that one. We've played around with array 2Ds and 2D matrices for a lot of the puzzles. Let's use a map for this for day 16. So let me grab my input. It's 110 by 110, and the example is a bit smaller. So back to our old habits of parsing and then solving. Does it make sense to parse a lot? Those mirrors, I actually like the visual representation. Yeah, let's just parse, but let's not parse into a union type per se. Let's just parse into the characters. That's good enough. I like the visual aid that these characters give us, and it's hard to do that in a union type. Okay. Okay. Let's parse. So approach, we are going to parse this into a map that maps coordinates to things at that coordinate if we have some. So if we don't have anything in origin in 0, 0, we don't have an entry in the map. Our XY coordinates, X grows to the right, Y grows downward. I think that's the most used approach. Let's do that. So what is our device called? Or what is our grid called? The contraption is a 2D grid. I'm just going to call it grid. So let's parse the grid. We need rows and columns. So let's iterate over. Let's iterate over lines here. And I think I did a whoopsie. I did a whoopsie. So yeah, let's iterate over our lines. These are the Y coordinates. So I'm going to use a list comprehension again. I would like the row number. And I would like the row, and those are in input. And if we index that, we get row numbers, and then we can do the same for the columns. Row, and we can yield row num. That's the x coordinate. No, column num is the x coordinate. I'm notoriously bad at x, y, column row things. So column is x, row is y. Yes, and we also return the cell, but we only do that if we have something. So let's wrap an if around, and if we wrap an if around, we can't just use the arrow. We need to do a yield. Why is this not correct? Because we also need to index the row itself to get our column numbers out of there. What's the problem? Expecting a function that take... Ooh, what? Row is a string? Oh yeah. And a string is a sequence of things, not a list of things. So just to index and to iterate over it, we can use the sequence module. Let's keep it symmetrical. There we go. And I would only put in non-empty things in there. So if cell does not equal the dot, then we yield. Otherwise, we don't yield anything. This is now a list, a flat list of coordinates and cells, or non-empty cells. If we just smoosh this into a map, we have a lookup table. So this will return a data structure we can use. And let's test it out for our example. There we go. So we have a lookup table that maps coordinates or potential coordinates. And if there's something at that location, we have a hit. So on column 0, row 1, we have a vertical splitter or horizontal splitter, depending on how you look at it. Yeah, that's correct. And in 1, 0 we have as well. And on 1, 2, 3, 4, 5, 0, we should have this. Let's verify that quickly. So let's look up, what was it, 5, 0? Yeah, so that's the mirror tilting left a bit. Okay, so I think we are good to go. Now, we need to start emitting our beams. Beams have a direction, and beams change direction. If potentially change direction, they potentially split into multiple beams. So yeah, let's introduce some types. A grid, let's just alias that as a integer tuple. as keys, and the values are just characters. And our beams, what's a beam? What do we need to keep track of? The location of a beam. Let's maybe alias location as well. So grid maps locations to the things at location, and a beam is some kind of data structure that knows where it is and has a direction. So it's going in some kind of direction, and it's just the 4 orthogonal directions. So it's north, east, south, west. That's good enough. I think the example talks about upward, downward. Okay, let's do left, right, up, down then. Better. So that's a beam. We start with one beam, but the beams can multiply or split. And we have cycles. So this sounds like a breadth first or a depth first search with cycle detection because we hit potential cycles. Yeah. Okay. So. Let's start with this, just a single beam, and see how far we get. So we start with a beam. Is the top left thing in our grid always empty? No. So our beam actually does not start at origin, it starts at 1 to the left of origin. So I'm already going to provide a list because we know that beams can be split into multiple beams, and that's the only state right now I'm keeping track of, which is all the beams that are currently in flight. So this first beam starts off at 1 to the left of origin. So this is origin, and if we want to go 1 to the left, we shrink x by 1. And the direction is right, sorry. So this is our starting state. We have the grid and we have a beam, and what should happen or what can happen, we just take one of the beams, or we take the first beam, whatever, and we move that beam as far as it goes until it either dies out at the edge of a grid like this, or until it hits a location we already visited, and we need to take the direction into account because beams can cross, and that should not short circuit the search. So if we pass a cell or a location in exactly the same direction as we did once before, we know we're doing work that has already been done before. We could optimize it even a bit more, but let's not think about optimizing it even a bit more. Let's just start there. So we also have like visited nodes, and that is a set that maps locations and directions. So it's a combination of both, and that we can use to detect cycles and not do twice the work or keep doing the same work. Okay, now next step, this beam needs to start moving. We could move it in very big steps, or we could move it pixel by pixel, or location by location. The location by location thing sounds easiest, so let's start there. How do we figure out the next location of a beam? So let's grab beam and let's figure out next. That needs to take into account the direction of the beam and the location, so we can just... Yeah, let's write the helper function, next location for the beam. And that returns a location. And it takes a beam, so let's put in some type hints. Yeah, let's just pattern match on direction. So we have X, Y, which is the beam's current location, and we pattern match on beam's direction. Right is easiest in my head, so if it's right, we +1. If it's left, we -1. If it's downward, we increase y. If it's upward, we decrease. This is something we've written a lot in all those Advent of Code years. So that's the next location. I think that's correct. Let's not use the same name for our variables and our function names. Let's maybe try 1 or 2. So next location for a beam at origin. Facing whatever, downward. So let's call our shot here. That should be, what should that be? It should be growing y by 1. Yeah, okay. I think this will work. No, test is not defined. Oh, I need to send my unit test runner or my unquote to the interactive window. Yeah, okay, so this works. It looks symmetrical, it looks correct. That's enough assurance for me. So we can find the next location of the beam. If we already visited that next location with this direction, we're done. So if it contains the next location and the beam's direction, we're done. Otherwise, we need to do something. I did it again. I pressed save. Okay, so something like this needs to happen. What do we need to keep track of? Actually, we need to find all energized. We need to find all energized grid cells. And if we are done with this one beam, we need to continue with the next beam if there are any. So let's start writing some kind of function. What are we doing? We are emitting beams. Yeah, let's call it emit beams. Taking beams, taking the grid. Yeah, why not? Taking the beams and taking the set of visited nodes. And this is the start of the visited nodes, and we can pattern match on the beams. Yeah. So pattern match on beams. No more beams means we're done. Means give me everything we've seen up. Yeah, give me every cell that we visited. Some beams. Then we need to do something, and then I think we can start using what we have been cooking up. So this is then beam. We figure out the next location if it's in there. Then this beam is done. We need to do do the recursive thing for the rest of the beams. We don't need to grow the visited set because we've already been there. Otherwise, we have not yet seen this location in this direction. Then it depends on what's on that location, right? So what would we like to do here? We would like to figure out what happens to the beam. Maybe it splits in two, maybe it just passes through, maybe it's out of bounds. So we need to do something like that. I don't know if we need to extract a function, and if I don't know, I just like mosey along. So let's just mosey along. So what do we need to figure out? What's at this location? So what is at next? And we need to ask this question with the grid or corresponding to the current grid. So let's cook up a function that takes the grid and the location and gives us our value. It's just a map.lookup, but I like to keep like the details that we're using a map. I like to keep that limited and not too visible in my algorithms. So let's write a wrapper function. An at, yeah, why not? So at next. And just to satisfy the compiler, let's also return some kind of set here. So at does not exist. Maybe let's put it in a grid module. Let's put it in a grid module. So module grid, and we have a add function which takes a grid and location, and it returns whatever. Not whatever, but it returns something. There we go. There we go. I see some unused things here, so let's pull those down. And let's run our thing. So it's what? Emit beams on the grid in the empty set with our starting beams. Let visited cells equal listing. That's what we're doing. And that's what we'll be running in a second. Okay, so back to the add function. Which is just a lookup, right? And that can fail. So it's actually a map.try. And that gives us an option of a character, right? I think that gives us an option of a character. And we need to swap grid and location to make it pipeline friendly or friendlier for the pipeline operator. There we go. We can pattern match on this. Yeah. What does it mean if there's nothing at this location? The beam has basically hit the edge, right? Or no, it might have hit... Ooh, that's bad. It might have hit an empty space, or it might be out of bounds. We have no way to make the distinction right now. So yeah, let's not forget about empty cells. Let's very much keep track of empty cells. There's multiple ways to do this, but I think if we just do this, then I think the map has zero use, and we were better off maybe using a 2D array. Except maybe the out of bounds checks. Now it's still this, and I think if we use array2d, we need to do some out of bounds checks. So yeah, I'm still happy with it. But again, now empty stuff is in the grid, so that means if we hit a none, we do not know about this location, so we are out of bounds. If we are out of bounds, this beam has run its course and we just continue. Do we want to keep track of out of bounds things in our visited sets? No, we do not. So I think we literally do this. Same recursive case. We continue on with the same grid with an unaltered visited list and with the rest of the beams. Cool. If we found something. It depends on the thing we found, right? If it's an empty space, we can just go on with our recursive call, but visited grows. Let's maybe do some in-betweens here. So the new visited is the original, but we add the next location and the beam's next direction, which is the original direction because we hit empty. So yeah, that's the next set of visited nodes. Nope, we need to write next visited. Those are this is where bugs occur. So yeah, we have visited, grid, and then we need a beams list. What is it? It's the rest of the beams, but this beam is still traveling, right? I'm just gonna plug it in. So it's the original beam but we change its location. To next. Is that correct? So we figure out the next location. The direction stays unchanged. Yeah, okay, if we hit empty, we have visited that next location. And we run the algorithm with the beam that ticked one to the next location. I think that might be correct. Famous last words. Okay, so what happens if we hit... let's take the mirrors first. Yeah, let's take the mirrors first. So we have our two mirror directions, right? It's this one and this one. Don't like the... That's not visual anymore. Can we do... No, it's a character. It's not a string. We can't do much more than escaping it. So yeah, let's escape it. And then our splits, our splitters, they are something like this. And if we hit anything else, we just crash. This should never happen. Unknown cell. Ooh, I'm looking for percentage, not ampersand. It's there. Okay. That's shouty. This is better. Okay. So yeah, these are all the arms we need to fill in yet. And if we've done that, we're almost done. Minor detail of filling in these arms. What happens if we hit a mirror? No matter what direction we are currently facing, we change direction, right? But for the rest, everything stays the same. So I think we can do also this, but instead of only changing the location, we also need to change the direction. We need to rotate a bit. So yes, we need to update the visited set, but we need to also rotate. So let's figure out next direction. Again, is that a band? No? What's the One Direction? That's the boy band, right? Yeah, okay. So next direction is safe to use. Cool. So we need to rotate our current direction with regards to this mirror. Okay. Just going to write a helper function for this, which is an exhaustive pattern match. Does that belong to a module? Nah, let's keep it. We have a next location right here. Let's do a next direction. Yeah, that makes more sense. Next direction given... Yeah, why not give it the beam? No, let's give it the location. And mirror, let's give it a mirror. And it returns direction. It should not need the location, sorry, it needs the direction. That's a hard word to type apparently. Okay, there we go. Yeah, so it gives us some kind of direction, and instead of rotate, we renamed our function mid-flight. And we take a direction in the mirror. What's the most logical order of arguments here? Next direction, given a direction and a mirror. Yeah, sure. And if we know this, we can... Is it comma? No, it's semicolon. Cool. We update every property of beam, and then apparently we do not like using the with the record update syntax, so let's not do that. Okay, fine by me. Formatting wise, a lot happened, but I think it's okay. So let's look at this main algorithm. Update visited. Update the next direction. We need to rotate, yes. And then continue on with this newly moved, rotated beam. Sounds correct. So let's do the actual rotating by using an exhaustive pattern match. Why not? So let's match on mirror and direction. What mirror are we doing right now? This mirror. If we're currently facing upward, we need to go rightward. If we're facing downward, we need to go left. If we're facing right, we need to go up. If we're facing up, down, right, left, we need to go downward. So this is for the mirror in the one direction. Let's just duplicate and do it for the other mirror as well. We can plug that in a second. And let's verify this. So if we are here, we're coming in from above, we should be going to the right as well. That sounds like a bug. Oh, sorry, yeah, we're not coming in from the upward. We are traveling upward, so we should go to the left, yeah. Oh, what happened? There we go. If we are traveling downward, we should go to the right, yes. If we're traveling to the right, we should go downward. Yeah, okay, so everything changes. Everything is symmetrical. I have a good feeling about this. And in all other cases, we expect something else, or we expect only mirrors here if we're doing this. Actually, we could fall back to whatever direction. Just keep continuing, and then I think we could also make our code more symmetrical, because now here we could in theory also update the direction, and every arm starts to look very much the same. That could also be an option. But okay, this is digressing a bit. This is the case for this mirror. I think for the other mirror, it's exactly the same, except we rotate in another direction, yeah. So I'm not gonna think too much about cleaning it up. I'm gonna make it work first. And the only thing that changes in this arm is it's a different mirror. Maybe let's make that a bit clear. Nah, it's okay. So yeah, those two arms should handle our mirrors, which are pretty basic. This is where things get a bit interesting, or it's a twist. We are like splitting beams, or potentially splitting beams. So what would this look like? We visit this node and we split into two versions of this beam, one facing up, one facing down. I think that would match with our algorithm nicely. So yes, we are continuing on with the search. So we need to recalculate the next visited by adding our current beam, yeah, in the next location, which is the location of this pipe, yeah. We do not need to figure out the next direction. We know very well what directions our two versions of the beam have to go. It's up and down. So we call ourselves recursively. We have updated the visited set, and instead of doing this, we need to go there and face up once and do the same but face downward. And we can, I hope, oh, sorry. We can, I hope my auto formatter will help me here. Yeah, no, what's wrong? Oh, semicolon, that's what's wrong. Okay, formatter, help me out here. Okay, there we go. So yeah, we visit our, this is already a bug, but okay. So if we visit the splitter, we should not always split. We should only split if we hit this splitter from the side, not from the pointy end. Yeah, So that's something we need to fix here. So if our direction is up or down, so if we're up or down, then we do something stupid or trivial, and otherwise we do what we're doing here. We split into two different beams. Yes. What happens if we're coming from up or down? We just do it as if we are visiting the empty space, right? So we say update the visited set and continue while ticking to that location. Yeah, I think that's correct. For our horizontal arm, it will be very similar, but not the same. What the? Wait. That looked as if I pasted way too much. So let's take this arm once more. No, it's just weirdly formatting. Okay, there we go. What changes when we shift from vertical splitter to horizontal splitter? Need to update the visited set. Yes. If we're in left or right, we just pass through. Otherwise. And now we need to split to the left and the right. We update our visited set. Yes, we do, I think. Maybe. Hypothetically speaking, this could be our first attempt at the algorithm. So let's give it a try. Okay, we get something. And we get a lot of coordinates that we visited, but we also get like, this was the direction a beam was facing when we visited this cell or this location. And that's not really something we're interested in. For example, this 2 here, we have a downward facing beam and a leftward facing beam. We don't care. We just want to know, has this location been activated? So we can say visited cells, just give me the coordinates. Just map me to the first thing, and I think that already dedupes because we stay in a set. Why is this not working? Okay, it's working. So it's unique visited locations. It's just converting that thing that knows about the directions to a thing that only knows the locations. And because we stay in a set world, it dedupes and we don't have duplicate entries. And counting the amount of energized cells is actually, or tiles, sorry, is a, we should see 46 here. So that should be number size. Size sounds better for me. What? It's saying like, okay, you can use same as size. There's no size function. What is this? That's interesting. What was the actual thing count? Okay, sorry. 46. Yeah, that looks correct. Happy. So I think this is our solve function for today. So let's wrap it in a solve function. Let's have it work on input, the argument, and I think we can just solve the example now. No, made a typo. Oh yeah, we need to return something, sorry. The amount of energized tiles. And let's make it very clear that we're returning the amount. There we go. So this solves our example. We can plug this in as a test. It's like some kind of trivial test and then, okay, this is the solution to part 1, nothing in between. Okay, so let's solve our input. Our input, do we have a correct input? Yeah, I think so. And let me put that at the bottom. Let's maybe put on some timings here. It's not too bad. 100 milliseconds. And it is even correct. Yay, yay for us. Mini round of applause. Let's take a look at part 2. If part 2 gets too hairy, I might split this video into 2 parts. But let's first take a quick peek at the problem. As always, there we go. We can forget about the first part and hack away for part 2. What does part 2 ask of us? As you try to work out what might be wrong, the reindeer tugs on your shirt and leads you to a nearby control panel. There, a collection of buttons lets you align the contraption so that the beam enters from any edge tile and heading away from that edge. Okay, we can hit from any edge tile. Interesting. If it starts at a corner, you can choose either of 2 directions. If we start at the bottom right, it can start heading either left or up. Okay. Okay. The beam could start on any tile in the top row, any tile in the bottom row, any tile leftmost, or any tile in the rightmost. And we have corners. To produce lava, you need to find a configuration that energizes as many tiles as possible. That's a cool twist, actually. I like it. And I think it might be trivial. Or not trivial, but I think it might be easy. Even on the corners, we can just plug in the 2 corner bits. Yeah, I think we're good to go. So we need to find out the configuration that energizes as many tiles as possible. And for the example, we have some kind of ideal start location, 4th tile from the left in the top row. This one? No. Where is the beam? 4th tile on the left in the top row. 1, 2, 3, 4. This one? Probably this one. And then it shoots down, it splits, and explosions happen. Okay, so we can run our part 1 algorithm, our search algorithm. We can run it for all the possible starting locations of the beam. And then just count it up as we do for part 1. That's a basic extension of part 1. Famous last words again. But how big does this scale the problem? We did just 1, and now we're gonna do 110 times 110. Or what's the circumference of a 110 by 110 matrix? Just doing this 4 times, right? Wow, it's only increasing by 400 times. That's, yeah, we're good to go. Only thing about the directions, how do we generate like all starting things? If we just take a look at every direction, we'd like try to shoot all beams downward and then try to shoot all beams leftward, we get our 2 entry points for this cell, right? We get the upwards and the leftward. Yeah, so we just need to iterate over all our edges and hit in from the right direction. So how do we do that? We can just generate those coordinates, right? It's the one on the first row, it's the one on the last row, it's the one on the first column, it's the one on the right, last column. Yeah, we can just generate these edge coordinates. And I'm pointing at these, but it's actually everything around it, right? We started -1 for part 1. Let's keep doing that for part 2 as well. So let's first generate everything on the left of the grid. That's most similar to our initial starting location here. So I'm gonna call our solve here something else. I'm gonna call this, or actually, let's extract a function here. So start is something that will change. We need to do that a lot. Visit is something that will change. Yeah, okay, I'm not gonna worry about it. I'm gonna play around with the problem some more before I start thinking too much about how we should extract our function and stuff like that. So let's first try to actually generate all the starting locations or possible starting locations for our beams to find the optimal configuration. So we have a grid. Let's drop back to the example. And let's calculate all starting beam locations. So right now that is just this one, but we would like a lot more starting locations. Or we would like to loop over a lot more starting locations. We need to figure out the length or the dimensions of our grid, right? Let's just do that on the raw example. Because our grid is already a map. Yeah, let's do that on the raw example. So let's extract dimensions. Width. Let's first take a look at width. Or height is simpler. Let's just example count the number of rows. And width is, let's just grab something and figure out how long that is. And they're probably squares. Yeah, I think the input is squares as well. Let's make sure it's 1 by 10. Yeah, so, okay. Let's call it the dimension of the grid. So that's the width and the height. And it's 10, so now we can generate all those starting locations for the beams on the left. And that is from 0 to dimension -1 probably. Yeah, and then we can generate some starting beams, which start at, sorry, this is a map. They start at all at -1, but the row index is whatever we generated here, so that's a row. And let's plug that in. And all these locations. Let me first close up my parentheses. Okay, yeah, all these locations are facing right because we are at the left of the grid. Why is it still not happy? Okay, it is. It just took a while. So these are all the starting beams to the left of my grid. Okay, now we can play around with our solve function. So these are, what's it called? Starting beams. Let's call them starting beams. And this is just the ones to the left, but we can grow or we can evolve this to all the edges in just a second. If we have this, we need to do our solve a lot of times, basically, right? And this all remains the same. So I'm just gonna call solve using a grid already. And a starting location, yeah. So it takes a grid and a starting beam. Yep, it takes a grid and a starting beam, and we plug that in here, just as we did before. Why the squigglies? Okay, so this is solve for one beam. And if we have some starting beams and we parse our grid, we can say solve on the grid for all our starting beams by using a map. And we just plug in our solve function, and this gives us the energized tiles. Calculate and number energized tiles for a starting beam. So yeah, this is where we're heading. And these are the number energized tiles for those starting locations. Let's see if this actually works. So we have, instead of one starting location, lots of starting location. multiples. And let's see if this works. We get a lot of, we get 46, which was our initial thing. That's why the number is ringing a bell. But we expect for part 2 to find our winner right there, right? And that should be 51. So let's now calculate the remaining edge beams. So these are all the ones to the left. I think we are very close to generating all the ones to the right as well. What are the coordinates? Instead of -1, they are 10, right? I think so. I'm gonna do something, no, I'm not gonna do something stupid. I was thinking of maybe let's flat map and provide 2 starting beams, but future me will not like that. Let's just union. What's a union? Can we not list union? We can append multiple lists. Good enough. So yeah, I'm gonna extract this into the left edge beams. Left edge. And I'm gonna just append all those things together. Okay, yeah. So that's the left edge. Let's take the right edge. Now that I see this, I think we can say left edge, append, right edge. I think that's the append operator in F#. Concatenates 2 lists, yeah. Why is it not content? Oh, sorry. I typed left edge twice. Okay, so everything stays the same, except instead of -1, it should be dimension, which is 10, right? And 10 is correct. And instead of facing right, we should be facing left. I think these are our right edge starting beams. And now let's take our beams on top. That means going from 0 to 9 again. Yeah. So top edge. That means going from 0 to 9 again. And our row should be -1. So our row should be -1. Our columns should be whatever we have here. So these are columns. Did we mess up here? Are these rows? Yeah, I think so. So on the left edge are column. Is that correct? No, sorry. Those are the top edge. I'm so bad at this. I'm so bad at this. So yeah, on the top edge, we are at row -1 and our columns are 0 to 9 and we are facing down. And we can just add these to the starting beams. Cool. Almost there. Bottom edge. Just in case our solution lies at the bottom. Same thing, except this should be dimension, right? And we can just plug that in. Cool. Very straightforward. Very basic stuff. Let's see here. We should find the number, what was it? 51 in there. So let's find our max value. $51 is in there. Would you look at that? Okay, I think we have our solve down and it should be 400 times slower or maybe a bit more if we have some crazy stuff going on once we hit our grid from different directions. But I think we might be there. Let's write another solve function, right? And that just does whatever we've been cooking up. And we return our energized tiles. And we can solve the example. And let's pull that up again. It's 51, that sounds correct. So That should be 51. We're good to go. We're good to go. Let's just make sure that I'm using the input argument. That's something that has tripped me up multiple times before. So our solve function takes whatever and it uses whatever. So let's use something less biased than the word example. We are using it at multiple places, right? We are also using it to parse, yeah. No, let's keep grid there. Yeah, okay. Why am I randomly changing stuff? Let's just run it on our input, right? We have been going for 55 minutes. It would be awesome if we finish day 16 under an hour. Sorry. Timing is on. Let's take a look. Ooh, it's heavy. Did not expect this. Huh. Interesting. Okay. 13 seconds is not good, but I have committed greater sins. I will not be optimizing day 16. Or at least not if this is the correct solution. So yeah, let's take a look. I don't know why it does that. If I auto format, poof, it changes up. But we have a number. Let's see if it's correct. Pretty straightforward, but again, I love today's puzzle. Cool. Time for a quick recap, and then we can all go and enjoy our weekends. So we did some beam traversal today. We worked on, or we first decided that we would use maps instead of 2D arrays. And the only reason I like to do that is because for arrays you need to do out of bounds checks with your indices. If you use a map, you can just use the try find thing that we do here. You could also define your try find for array 2D, sure. But this also works. Maps are a bit slower because they need to do hash map lookups. We saw that yesterday, right? So they need to do some extra work next to array indexing, but I find them to be a great trade-off if the performance is okay enough. And arguably performance was not okay today, but it's good enough for Advent of Code for me. We defined some types. Apparently we never used the type. Let's fix that. Let's use the type. So our parser returns a grid. There we go. Now the rest of the type inference kind of knows that we're using grids everywhere. Cool. Again, we did the module and the type hack to scope functions to some types a bit closer. We did not parse our cell contents. We just used this because it's very visual. If you look at this, you know what kind of mirror. If it's like a textual description of this mirror, you lose some context. But then you cannot exhaustively pattern match, and that's the trade-off we're making here. So our algorithm was basically a depth first search, and the twist today was, or there were two twists. The first twist is that this just bounces a beam around and changes its direction. That's not too big of a problem, but we had some interesting grid elements, these splitters, where you sometimes just pass through and sometimes your beam splits in two. That's a nice twist, like that one. And we just keep our breadth or depth first queue. We just add in the elements of the split beams, so our algorithm continues. There were cycles in the example, so there's probably cycles in mine and your input as well. So we are keeping track of all the nodes we visited, including the direction we were facing at that time, because location can be visited multiple times in different directions, and we should follow through on all the paths. We can't just drop one because we've already been there. And then, yeah, we used recursion. We used the full power of recursion here. I think it's pretty clear. If you know the problem, you know what we're doing here. There could be some, or there's room for extracting some duplication here, but I kind of like it. It's very clear. It states if we encounter this, this is everything that happens. I'm not gonna bother by cleaning up. I think it's good enough for today. And then we just needed to see how many locations our beams touched, which was this dedupe, because our visited set contains multiples, and then just counting them, so that was okay. And then for part 2, there was this twist where we did not have a single starting beam, but every possible edge. That was a cool twist. We just generate all those possible starting locations, and we ran our original algorithm a whole lot of times, which is what we see here. And we just found our winner. So yeah, really liked today's puzzle, and I hope you did too. This is all I have for Advent of Code in F#, and I hope to see you tomorrow for more fun. Bye bye.